All right. So it's great to see everyone. Sorry I couldn't make it in person. It sounded like a really exciting meeting. So today I'm going to talk about this particular piece of work. And the motivation for this work is that there has been a lot of theoretical, observational, and modeling studies thinking about submesoscale dynamics from a local perspective. So thinking about how local processes alter submesoscale fronts. So for example, this is a very different topic than the previous one, but just switching gears. And we can think about how submesoscale straining impacts, mesoscale straining impacts submesoscale fronts. Also, Ekman effects impacts submesoscale fronts and different processes of mixing on the frontal scale and how that changes those fronts, and also mixed layer baroclinic instability and how those impact submesoscale fronts. And so this kind of has been, it's still an area of very active research, but a lot of people have been sort of tackling submesoscale frontal dynamics from this perspective. So it is what we've been doing for the past couple of decades. And what I'm interested in is thinking about the global scale, ocean, and climate, and trying to link submesoscale frontal dynamics to what's happening on the larger scale. And there has been some work looking at this. Usually it's happened from sort of this perspective. So thinking about how submesoscale frontal dynamics impact regional and global scale ocean and climate. So things like, how does mixed layer baroclinic instability alter the mixed layer properties and restratification properties in the ocean, and how, to the extent that it impacts the larger scale? Or how does submesoscale dynamics, for example, instabilities along fronts, mixing along fronts, impact things like heat flux on a global scale? So there's been a little work there. It's still pretty open. But I would argue that there's been very, very little work thinking about how the regional and global scale ocean and climate alters submesoscale frontal dynamics. And this is the gap that this the study that I'm going to be showing you is aimed to fill. All right, so we're going to look at a couple different questions. The first is, what dynamics govern submesoscale fronts globally? And the second question will be based on a number of different data sets. So, for example, this is Argo data, where I calculated the mixed layer depth and also the mixed layer buoyancy frequency, which I've defined as the upper 3/4 of the ocean, the average buoyancy frequency in that region, and also the large scale horizontal density gradients and the large scale horizontal Turner angle. So negative values indicate that the large scale gradients are salinity dominated versus positive values indicate they're temperature dominated. And we're going to use all these things to answer the question, what role do these climatological variables play in setting the observed submesoscale frontal dynamics and spatial variability? All right, so the next step is we need to look at and find some fronts observationally. So what I've done is taken a global database of temperature and salinity from ships driving around the ocean everywhere, and I've identified fronts. And then what I've done is I've calculated the orientation of these fronts and therefore their width and density gradient using two different approaches. One is a statistical correction, assuming a field of randomly oriented fronts and also ship tracks. And the other one is a satellite correction, where I use sea surface temperature data to correct for the correct orientation of the front. And I can do that for 1 of every 10 of my fronts. And then what I can do is I can calculate the buoyancy gradient across the front, and then do some statistics on that and say, okay, this method detects fronts typically 1 to 10 kilometers wide, and it has often buoyancy gradients of around 10 to the -6 to 10 to the -7, sometimes stronger gradients all over the world. And then I also wanted to figure out a way to kind of conceptualize what I've observed. And so what I ended up doing was I used one of the underlying assumptions from quasi-geostrophy and said that the Froude number is approximately scales with the Rossby number. And then I also included a measure of sort of the ratio between the different buoyancy gradients, the horizontal and the vertical. So that's the balanced Richardson number. And then I combined all those things together and came up with a scaling that suggests that the buoyancy gradients across the front scales with the frontal width and the mixed layer depth, and also the balanced Richardson number and the Coriolis frequency. And then what I can do is I can take all of my fronts and plot them according to frontal width, and then compare that with the scaling, and then with a fit to the balanced Richardson number. So I'm fitting essentially the x-intercept, or sorry, the y-intercept for this log-log plot. And I find that the scaling represents the data pretty well with a Richardson number of around 1. So that is encouraging. So this can be used to say, okay, this describes the dynamics of submesoscale fronts globally. The second thing I can do is look at the spatial distribution of the frontal gradients globally. And we see that there are sharper submesoscale fronts in places like the western boundary current extensions, in places where there's seasonal river output, and also along coastlines. And so there's definitely spatial variability of these fronts globally. And then we can use this spatial variability to ask the question, what role do these climatological variables that I mentioned earlier play in setting the observed submesoscale frontal dynamics in spatial variability? And the first thing I'm going to look at is the large-scale horizontal density gradient. And you can see here, as you increase the large-scale horizontal density gradient, the submesoscale frontal sharpness also increases. So this is true globally and also in most latitudinal bands that I've chosen as well. And so this indicates that when you have larger scale density gradients then you also have smaller scale fronts. And it could be because a combination of reasons. One is you have more kinetic energy when you have large scale density gradients, which could be associated with smaller scale gradients. The other is any kinetic energy you do have will stir the large scale gradients and cause smaller scale gradients. And then we can combine this information with the cause of the large scale gradients. So here is including the large scale horizontal Turner angle. So as a reminder, negative values indicate that the large scale the large scale density gradients are dominated by salinity, and positive numbers indicate that dominated by temperature. And we see that the fronts are not as sharp when you have large scale gradients that are dominated by temperature, and they're sharper when you have large scale gradients, like in the Bay of Bengal, dominated by salinity. And you find especially sharp fronts when you have both salinity dominated and really strong large scale density gradients. The next thing I can look at is mixed layer depth. And this one is a little bit more complex. The overall pattern is that you see sharper fronts when you have shallower mixed layers globally in general. And I suspect that this is partially due to the kind of looking back at the scaling that I showed earlier. And so just because H is on the bottom of the scaling, as you decrease the mixed layer depth, then you increase the horizontal buoyancy gradient across your front. So it's consistent with our assumptions that are underlying QG dynamics. And also, I find evidence for a modulating effect. So because if you have really shallow mixed layers on average globally, your n squared is larger, and therefore your balanced Richardson number is larger. That would decrease the horizontal buoyancy gradients associated with the submesoscale fronts. So it looks like there's a main effect and then also a modulating effect as well. And we also can kind of divide things up according to both the large scale gradients and Turner angle and also the mixed layer to sort of get an idea of what sort of different regimes of dynamics we have globally. And what we see is that when we have deep mixed layers and very temperature dominated large scale gradients, like in the middle of the basin, North Atlantic, you don't really have very sharp fronts. But in places like the Bay of Bengal, when you have salinity dominated and areas and shallow mixed layers, you have really sharp fronts. So they have very different kind of environments. And we can also look at the kinetic energy. So here I've approximated the kinetic energy at the fronts by looking at just the geostrophic component and then averaged it over the entire mixed layer. And what we see is that because of the importance of the sharpness of the fronts in this quantity, you have, for the same mixed layer depth, you have higher values of the average, the total kinetic energy. So you have higher values of the total kinetic energy at a certain mixed layer depth when you have salinity dominated large scale gradients opposed to temperature dominated large scale gradients. So to put that in a little bit more concrete terms, if you compared the Bay of Bengal with a place with a similar mixed layer depth that is more temperature dominated than salinity dominated, we'd expect to have lower values of the geostrophic kinetic energy associated with the submesoscale fronts. So this kind of gives you an idea of, okay, we have very different regimes, and places like the Bay of Bengal are very different than a lot of the places that have been more heavily studied, for example, in the North Atlantic. All right, so in conclusion, what I've shown here today is I've shown a look at submesoscale fronts between 1 and 10 kilometers wide. And I've shown that they scale according to my scaling, which is based on underlying assumptions behind QG. And this suggests that on average, in a very average sense, we don't have extremely strong ageostrophic fronts on a global scale. And I also show that the buoyancy gradients associated with the submesoscale fronts vary globally, and that sharper fronts are associated with shallower mixed layer depths and are modulated by variations in the balanced Richardson number and n squared. And I also show that there are a number of different regimes on a global scale that have a very different submesoscale frontal dynamics. And this is really important because if you just go out and study one regime, then you're getting an incomplete picture of what's going on. And to kind of bring this back to the original motivation, what I was trying to do in this talk is to link the regional and global scale climate and ocean dynamics to submesoscale frontal dynamics. And I developed a few different things. So a scaling that helps us conceptualize kind of the linkages between the large scale and the small scale. And also I looked at the large scale horizontal density gradients and Turner angle as well. So these are just pieces to start with, and I welcome other trajectories of research in this arena, especially in the theory and modeling realm, because I think there's a lot to do. All right, and I'll go back to my conclusion slide. Thank you so much.
Thank you very much, Caitlin, for the nice talk and overview of submesoscale fronts. Are there any questions here from the room?
Caitlin, can you hear me?
Yes.
I'm just wondering, more of a theoretical question, but you talk about, in your last slide, you talk about how the dynamics of submesoscale fronts seem to be more or less coherent with QG. But if I'm not wrong, when you look at a QG model of a front, it would suggest that the frontal sharpening kind of stops at the Rossby radius of deformation, and you need to go to semi-geostrophic theory or something more accurate to have a sharpening beyond that scale, right? You need this ageostrophic convergence to explain something that is at the width scale that you mentioned, right? 1 to 10 kilometers. So I'm just curious whether there's a contradiction here, or whether more accurate theories just retain enough of QG's results that it seems to be consistent with QG anyway. Also, I wanted to ask you how you defined submesoscale front width. Yeah, so those are my questions.
Yeah, all right. So the first question, yes, that's a very good question. I scratched my head over it for a while. And so I did kind of look down the semi-geostrophic, kind of looked in that direction and thought about how I would see that in my data set. And from kind of the scalings I was looking at there, it would likely be a very different relationship between the frontal width and the buoyancy gradients that I do see. So it looks like the observations support this scaling opposed to more of a semi-geostrophic approach. And so what I have to say there is that this is a global average. It's not looking at the really strong ageostrophic fronts only. And so I can just hypothesize as to why, but it seems like that you can have really strong interactions and more ageostrophic that could be more better described by semi-geostrophic theory in particular cases. But those cases I expect to have short time scales, and that may not be as important a contribution to the global average. But I think that there's a lot of work that could be done looking into this in more detail. So I think it's a very good question. And the second one, the frontal width. So I basically went around and I had this algorithm which looked for large gradients in the in between different data points in my ship track data. And so I looked for large gradients, and then I kind of looked for strings of those and did a bunch of sort of checks to see if they're actually a front. So essentially, I was selecting for places where you have definitely a front and weeding out places where fronts may not have existed. And so that was what I was doing to actually select for fronts. But the details are kind of long and maybe would be better, would bore everyone in the room. So that's a general idea.
Hi, I was just wondering if you had any insight as to why the frontal dynamics should care whether density is salinity or temperature. I mean, is it you're not thinking of double diffusion or anything like that, right? So why should it matter?
Yeah, so that is also another good question. So there's a bunch of different ideas. So I don't have a definite answer to that question. And I think that would be a great area of future research. but one possible idea is that temperature and salinity, when you have large-scale gradients of temperature and salinity, you're going to have different sets of air-sea interactions associated with that. And so any sorts of feedbacks would be different in the case of a salinity-dominated large-scale gradient versus a temperature-dominated one. So that is one set of answers. The other thing is that a lot of these salinity-dominated regions are river outflow, and so you're going to get it's going to have different boundary conditions and sort of different ways of sustaining the system versus large-scale temperature gradients, and so that could also play a role. But those are just ideas, and I think it would be great to really look into them in more detail.
So I was wondering, so did you also see areas where you have a total compensation? So basically no fronts, but temperature salinity compensation?
So the kind of machinery I built up didn't focus on that. But if you look at Kyla Drushka's work, she basically used the same data set and then calculated things. Instead of identifying the individual fronts, she looked at variance in the temperature and salinity, and then she looked at the Turner angle on those scales. And so she found different levels of compensation everywhere in the world based on that. And so I recommend, so the answer is yes, I didn't find it, but Kyla Drushka did. I believe her paper came out in either 2019 or 2018, so fairly recently. So I recommend you look at that to delve into that question.
Okay, thank you.
Mm-hmm.
Okay, we have one more question.
You hear me?
Yes.
So a great talk. So I just want to know, like, when we have this large scale freshening due to the melting of the sea ice or the glacier. So in those regions of the polar oceans, what is more dominating in terms of the large scale density gradient? Is it salinity or the temperature?
So let's see. So I did notice that at high latitudes, you have salinity dominated areas. So that's like the dark blue in those areas. I didn't look into this in detail, but I did notice that in places where you'd expect to have more meltwater from things like glaciers, then you have salinity dominated regions. I don't know if that's true on a kind of global scale or not, but that's kind of, I saw hints of that in my regime map here. So that's another great area of future research.
Cool. Thank you.
All right, I think we wrap it up. So thank you very much, Caitlin, again.
Thank you so much.
So